All right, so I think we should slowly get started. Any stragglers will come in momentarily. But so welcome to the last session of the RV for Autonomy Day. We saved, of course, the best stuff for the last. And it comes right after the exciting panel on RV for Autonomy. So we will complement these high-level opinions of big guys by cutting-edge research. So we have five exciting papers here. Um, so the first paper on actor-based runtime verification with Mesa, joint work by NASA Ames and JPL, will be presented by Nestor Chafier, and I hope I didn't mangle your name too much. So you all know the drill by now. The recorded presentation will play. Please feel free to put your questions in Slack, and after the presentation is over, there will be a live question and answer section. Please go ahead.
Hi everyone, my name is Nastar Shafi. I'm from NASA Ames Research Center, hired by KBR. I'm going to present the work Actor-Based Runtime Verification with Mesa. This is joint work with Klaus Haveland at JPL and Peter Mehlis at NASA Ames Research Center. This work presents our runtime verification approach implemented in a framework called Mesa. Our approach is based on using asynchronous concurrent monitors. Here in this picture, you can see a high-level overview of a runtime verification system that can be built using Mesa. The inputs to the system are a set of properties and a trace, which is a sequence of events obtained from the run of the system under observation. Mesa checks if the given properties hold for the trace and reports all the errors detected during verification. The use case that motivated this work is analyzing flight behaviors in the National Airspace System, called NAS. NAS refers to the United States airspace and all of its associated components, including airports, airlines, air navigation facilities, and so on. NAS is a highly distributed and large system with over 19,000 airports, and it could have up to 5,000 flights at the peak traffic time. Our goal here is to generate a monitoring system that can handle high volume of live data feeds and can be used as a ground control station to analyze air traffic data. Mesa is designed to target distributed systems, and itself is also distributed. One reason for using a distributed monitoring system is to improve efficiency, which is essential considering the use case that we are dealing with. Mesa adopts the actor programming model, which was proposed as a way to deal with concurrency in high-performance systems. This model allows for building efficient distributed systems, which is scale. In this model, actors are the primary building blocks. They're completely independent, they do not share any data, and they can communicate only by asynchronous messages. The actor model also guarantees that each actor executes in one thread at a time. So an actor can be viewed as a sequential program. In this picture, you can see the infrastructure of Mesa and all the systems which are integrated into the framework. And at the very bottom, you can see the JVM layer. So all the systems that you see here, including Mesa itself, are implemented in Scala. Mesa is built on top of the ACA toolkit, which provides the actor model implementation. Race is another system which is built on top of ACA and extends ACA with additional features, including mechanisms that can be used to connect to external services. Race is a framework which is designed to generate aerospace simulation. So when it comes to checking for properties in the context of NAS, some actors from Race can be directly used in Mesa systems. Finally, Trace Contract and DOT are trace analysis tools, which provide support for formal specification in Mesa. They allow for specifying properties in data parameterized temporal logic and state machines. These two tools are implemented as internal domain-specific languages written in Scala. To summarize, MESA is a framework for actor-based runtime verification systems. As you see in this picture, a MESA system is only composed of actors that implement a pipeline of 4 processing steps. The vertical lines between actors are publish-subscribe communication channels. You can see that outputs from one step are used as inputs for the next step. So the data acquisition step extracts data from the system under observation. The data processing steps parses this data and generates a sequence of events which are relevant to the properties. Next step is monitoring. The actors in the monitoring phase store monitor objects that capture the properties. So these actors feed their monitors with incoming events, and then the results from the monitors are sent over to the next step, which is reporting. So basically what MESA offers are the building blocks to create actors for each step of the runtime verification. As a basic optimization approach, MESA provides indexing, which is a restricted form of slicing. It slices the trace up into subtraces according to some specified data in the trace and feeds each resulting subtrace to the relevant submonitor. Dot also provides an indexing capability within monitors. It lets you define a function from events to keys, which are used to obtain those states that are relevant to the event. Using this approach, a dot monitor only iterates over an indexed subset of states instead of all the current states. As an additional optimization technique, MESA allows concurrency at 3 different levels. First, it runs in parallel with the monitor system. Second, multiple properties are translated into multiple monitors, one for each property. And third, each property is checked by multiple concurrent monitors by slicing the trace up into subtraces and fitting each subtrace to its own submonitor. Now let's look at our case study. We use MESA to check if flights in NAS are compliant with their assigned arrival procedure called STAR. STARs are standard procedures which are implemented by FAA for transitioning the flights from the en route phase to the phase where descent starts. Here is a STAR procedure designed for San Francisco Airport. A STAR specifies a set of routes, and each route is composed of a sequence of waypoints, which also come with altitude and speed profiles. In a way, a STAR is a form of a communication. So basically, when the air traffic controller gives a clearance to the pilot to take a certain STAR route, they communicate the route, altitude, and airspeed. So between 2009 to 2016, these procedures were implemented on an expedited timeline, which raised some safety concerns. That included unintentional pilot deviations, and that's the property that we check for here. Here is how we informally define the property. A flight shall cross inside 1 nautical mile radius around each waypoint in the assigned route in order. We formalize the property using a state machine which is implemented as a dot monitor. Here you can see the actor-based MESA system which is used to verify the property. We were actually able to detect some violation of the property. In the data acquisition step, the data is obtained from a FAA system called SWIM. SWIM consolidates data from many different sources, including flight data and weather data. Its purpose is to provide relevant NAS data to its authorized users, such as airlines and airports. In this example, we monitor flights that land at San Francisco Airport. So in the monitoring phase, we define 1 monitor per procedure, which checks for flights assigned to that procedure. Now let's see our experiments. The goal here is to evaluate the impact of using asynchronous concurrent monitors. We use the MESA feature that allows for using multiple monitors to check for a property. Here we check for another property in the NAS domain, which is called queue, and checks if the swing flight messages are ordered by their time tag. The reason that we check for this is that there were incidents that we actually didn't get the right ordering. This property is implemented as a data parameterized state machine in Dot. The problem here is this property is pretty simple and leads to a very small processing time inside the monitors, which is not ideal for the experiment. To address this issue, we use a feature in Dot that allows for defining a list of submonitors within one monitor object, where each submonitor captures the property queue. And finally, the events that are sent to the monitors in this experiment are objects of type state that captures the state of the flight, including its call sign, which is the flight ID, and the time attached to the message. Here you can see the different MESA systems compared in our experiment. I only show you their monitoring step here since they're only different in their monitoring phase. The first system called monitor indexing. It has only one monitor actor with one monitor object M that checks for all the flights in the input trace. It does apply dot indexing inside the monitor, which uses the flight ID in each incoming event as a key to retrieve the relevant states. In a way, this system resembles using the trace analysis tool, dot directly. The second system is dispatcher indexing. Here we have an actor called dispatcher. Dispatcher actors in MESA are configurable and used to specify how to distribute the check for a property. Here the dispatcher actor generates one monitor object per flight on the fly. It applies indexing on the input trace using the flight ID as the slicing criteria and sends each subtrace to its own monitor object. The third system, called concurrent. Here we have a dispatcher actor that creates monitor actors on the fly. If there is no limit set, it creates one monitor actor per flight, but we could limit the number of actors. So instead of one flight, the monitor inside each actor monitors a group of flights, and it applies dot indexing inside the monitor. The dispatcher also applies indexing on the input trace and feeds each monitor actor with its own subtrace. We ran these systems with an input trace including 200,000 messages from 3,215 different flights. This graph here compares the runtimes. The black line shows the runtime for the concurrent system where the number of monitor actors is set to 250. Meaning that each monitor verifies 12 or 13 flights. The green line is from the run where we have one monitor actor per flight, meaning that we end up with 3,215 concurrent monitors. The red and blue lines are for monitor indexing and dispatcher indexing, which both have only one monitor actor. The results show that the systems with concurrent monitors perform considerably better. You can also see that limiting the number of monitors to 250 improves the performance of the concurrent system. Also, the monitor indexing system performs worse than dispatcher indexing. Considering the similarities between their indexing mechanism, the difference mostly amounts to the implementation. We also obtained the CPU usage profiles for these systems by using Visual VM. These profiles represent the percentage of total computing resources in use during the run. As you can see, the graphs at the bottom, which are from the concurrent runs, have much higher CPU utilization, mostly above 90%, which is the impact from using concurrent monitors. Here you can see how the number of concurrent monitors impacts the runtime. We compare runtimes from the concurrent system using different number of monitor actors, starting from 125 monitors, where each monitor object handles a group of 25 to 26 flights, all the way to 3,215 monitors, where we have only one flight per monitor. The results show that using 250 monitors gives the best performance, and from there, as the number of actors increases, the runtime increases. Increasing the number of monitor actors decreases the load on each monitor actor, but it increases the overhead from their scheduling and maintenance. In our assessment, we also looked at different performance metrics for individual actors. We provide a mechanism to measure the average wait time for a message in the actor mailbox. Mailbox is a queue that includes the messages sent to the actor. We also measure the average time needed by the actor to process a message, called service time. These mechanisms come with some overhead, which is 20% for monitor indexing, 11% for dispatcher indexing, and somewhere between 20% to 28.1% for the concurrent system. Here the graphs in the first row compare the service time and the mailbox wait time for the monitoring actor in the monitor indexing and dispatcher indexing systems. These times are longer in the case of monitor indexing, which again the difference amounts to the indexing implementation. The second row shows these measures for the dispatcher actor in the concurrent system. Increasing the number of monitors increases both the service time and the wait time in the mailbox. In general, with more monitor actors, the load on the dispatcher is higher because it needs to generate and handle more actors. The third row shows these measures for monitor actors in the concurrent system. It shows that increasing the number of monitor actors increases the service time. Using more monitors decreases the load on each actor, but applying indexing inside the monitors that handle more flights improves the performance considerably, and it leads to overhead in the ones that track a small number of flights. Also, with smaller number of monitor actors, the mailbox wait time for the monitor actor is longer because each monitor tracks more flights, which leads to a higher arrival rate of messages and therefore a longer mailbox queue. Note that MESA is not really suitable for verifying hard real-time systems because it can't get control over its underlying layers, including ACA and JVM. Also, the default slicing mechanism in MESA doesn't allow for expressing properties that relate different slices. Here we present a generic framework for building actor-based runtime verification systems that employ asynchronous concurrent monitors. We showed an application of MESA on a real case study. Our empirical assessment also showed the impact from using concurrent monitors. It showed maximizing performance requires a limit on the number of monitors. We also identified various competing overhead resources that can impact the optimal number of monitor actors.
All right, thank you very much. So now it's time for questions. So I did not see any questions in Slack, still none. But I see some raised hands. So Joshua, can you unmute yourself and ask the question?
Yes, first of all, thank you for the talk. My question is, so it seems like these actor-based systems would also be quite useful for longer running monitoring of the system. But then there's the problem of fault tolerance, right? The machines on which the monitors could be running might fail at some point. Have you thought about how you could somehow make these distributed actor-based monitors more resilient against failures?
Pastor, did you hear the question?
Yes.
Okay.
Sorry, I was trying to unmute. So this is the so one thing about ACA is that there, for example, one issue with the monitors here are there is no guarantee on, for example, message delivery. So I haven't looked at making this fault tolerance at that point, but there are issues that we are dealing here with, like for example, in terms of increasing their reliability, there are we don't get support from the ACA layer, and there has to be some work around the actors that we haven't looked at that here.
Can I add something there? This is Peter Melitz, one of the authors. So actually, this is a strong argument for using ACA here, because there's this guaranteed strong supervision chain. So there's always an actor that's basically responsible for monitoring the actors under its supervision, which allows you to do fail-safe, failover implementation there. This means it could respawn the same actor. It could just create another one. It's up to your application to decide how to react, but you almost certainly will be informed if you have to react.
Okay, and if you would do a failover, how do you handle the state of the monitor?
That, for instance, could be done by transferring basically the state of a monitor actor from one to the next. So this is something. Well, there are different ways. So it could be a persistent actor. It could be something where you have, although this of course would kind of violate a bit the general actor idea here. Query basically actor state from the outside. There are ways around that, well, fortunately and unfortunately in ACA, so you have to be aware, but if you need it, you can actually do it. So the object still is around. It's just that the actor would not be able to respond to message processing in ACA anymore. So the actor object is still there.
Okay, thank you.
Any more questions? I don't see any raised hands. So let me ask a question. So you explored how different parameters of the concurrent deployment affect resources. So question is, can you be adaptive here? And if so, how do you specify what are your preferences for adaptation? Basically changing the number of actors at runtime or something like that.
So one thing that Meso provides is that you can, for example, when it comes to the number of actors that you can have at the runtime, so it's something that you can specify on the run. So based on your application, you can have algorithm to calculate that. But this is something which is different. It's really application specific. And so it's something that needs to be extended towards specific applications.
Okay, thank you very much. If there are no more questions, maybe we should move to the next talk. Thanks, Nastaran. All right, our next presentation is Runtime Safety Guided Policy Repair, presented by Wei-Chao Zhu from Boston University, and it's basically a collaboration between universities and Toyota. So sounds exciting. Please go ahead.
Hello, I'm Wei-Chao Zhou from Boston University. My topic today is focused on our publication in RV 2020, Runtime Safety Guided Policy Repair. It is a joint work from multiple collaborators. The direction of this paper is relevant to runtime safety of control systems driven by artificial intelligence. Our research is motivated by the accident in 2018. A self-driving Uber vehicle hit and killed a pedestrian in Arizona. It is important to assure the safety of AI-enabled autonomous system. To diagnose the safety issue of learning-based control system, we can take a look at this example. In the video on the left, an autonomous vehicle is driving in the city space at constant speed 8 meters per second while staying close to the middle of the lane as indicated by the green curve. The red curve is the trajectory of the vehicle. The control policy is learned from human demonstrations via imitation learning algorithm. Now we add an IC surface in the yellow rectangle as in the video on the right. then we can see that the vehicle skids out of the lane. The reason for this incident is that the vehicle has never been trained on the icy surface. This is a mismatch between the training and testing environment. This example suggests that runtime safety mechanisms are needed in learning-enabled autonomous control system. The researches on the safety of learning-enabled autonomous control systems have grown rapidly and diversely. For example, in the framework of constrained Markov decision process, safety can be encoded as costs. A safe control policy in the MDP incurs lower costs than unsafe ones. Formal specifications have been used to express the safety requirement on learning-based model. In our work published in CAF 2018, we use model checking to verify control policy against the specification written in probabilistic computational tree logic. We also use counterexamples to guide the training of the safe control policy. Model predictive control techniques have also been leveraged to determine if a candidate control action generated by learning-based controller is safe or not. There are also efforts on assuring runtime safety in a systematic way. One example is simplex architecture. The foundation is to pair the learning-based controller with the safety controller. The safety controller can take over control for safety when necessary. This architecture can effectively prevent unsafe outcomes at runtime. But a setback is that the intermittent and frequent switching between the learning-based controller and the safety controller can result in undesirable behaviors and reduced performance. And this is the very issue that we are going to address. Those are the contributions in this paper. Based on the simplex architecture, we propose the concept of policy repair for safety. It aims at improving the safety of the learning-based controller so that the switching between the learning-based controller and the safety controller can be reduced or even eliminated. Then we will show that a naive policy repair only for safety can potentially lead to performance degradation. Thereby, we introduced the concept of minimally deviating policy repair. It aims at reducing performance degradation in policy repair. Our approach combines learning from data with satisfying safety requirements. In the end, we validate our approach in case study. Here we introduce the background of the simplex architecture that we consider. The structure works in the environment in discrete time steps. At each time step t, the state of the system is xt. By outputting an action ut to the environment, the state evolves to xt plus 1. We assume that we have a dynamic model f simulating state evolvement. The structure contains a learning-based controller and a safety controller. The learning-based controller has a control policy pi theta 0 that maps each state to a control action. In the context of machine learning, this policy is a function parameterized by theta 0. Given the current state, the policy outputs a candidate control action to the safety controller. The safety controller is designed specifically for a safety requirement phi. In our previous example, the safety requirement can be if the vehicle is out of the lane, the vehicle should return back into the lane in 5 seconds. If a trajectory satisfies this safety requirement, then this trajectory is safe. Here is how our safety controller works. We call the safety controller PySafe, detects the current state xt and the candidate control action hat ut as the inputs. It works in 2 stages. First is the verification stage. It predicts if executing the current candidate control action hat ut in current state xt, whether there exists a trajectory in the future that satisfies the safety requirements. If true, then the candidate control action hat ut is certified to be safe, and it is taken as the output of the safety controller. If false, the safety controller enters the second stage, the intervention stage. In this stage, it solves a substitution ut for the candidate control action hat ut, such that there exists a trajectory in the future that satisfies the safety requirement. If ut can be solved, then it is taken as the output of the safety controller. If no such substitution exists, then a violation of the safety requirement is unavoidable. The whole system may have to halt. We use the model-based control to implement the safety controller. Then let the safety controller check every candidate control action at the runtime, can potentially cause overhead. The verification stage is inevitable, no matter whether the candidate control action is safe or not. But the intervention stage can be skipped if the input candidate control action is already safe. A straightforward strategy is to reduce the chance of the policy outputting unsafe control actions. We formally define this strategy as policy repair. Given a policy pi theta 0 paired with the safety controller pi safe, find a new policy pi theta star that minimizes the chance that the safety controller disagrees with the policy outputs. It can be also understood as minimizing the times that the safety controller needs to intervene. A naive implementation of this strategy is to use runtime data to train the policy, which we call naive policy repair. To do this, we let the learning-based controller to collect the runtime data. With the data collected at the runtime, we can obtain new policies via supervised learning. However, this simple strategy is flawed by potential performance degradation. We use a simple example to illustrate this. Consider a policy that was trained to steer a vehicle around a corner as shown in the first figure. When deployed in a slightly different environment, as shown in the second figure, the policy fails to keep the vehicle inside the lane. By pairing the policy with the safety controller, frequent switching between the policy and the safety controller can lead to undesirable behavior, such as the zigzag trajectory in the third figure. If using naive policy repair approach to learn from this zigzag trajectory, then we will obtain a policy that generates the trajectory, as in the fourth figure. We call this performance degradation. It is resulted from the repaired policy deviating too far away from the initial trained policy, as in the first figure. We can even quantify this performance degradation. The details are in the paper. This motivates us to propose the concept of minimally deviating policy repair. We provide this formal definition. Given the initial policy, pi theta 0, paired with the safety controller pi safe, find a policy, pi theta star, that minimizes the chance that it disagrees with the initial policy, pi theta 0, subject to the constraint that the safety controller does not disagree with the pi theta star, which implies that pi theta star should only generate trajectories that satisfy the safety requirement. Note that if viewing the minimization objective as an optimization problem, the decision variable is the policy parameter theta. However, in the constraint, the safety requirement is on the trajectories. The objective and the constraint are incompatible in their variables. Therefore, we invent an approach for minimally deviating policy repair. Firstly, we give an iteration for our approach. Suppose that we have a minimally deviating repaired policy. We would anticipate it to generate a trajectory such as the one in the fourth figure, because it is more like the first and the second trajectory which are generated by the initial policy. Our approach is then to iteratively synthesize new trajectories as the one in the fourth figure. This is done by transforming the minimization objective in the definition into an optimal control problem. The optimal control problem updates the trajectory tau of a naively repaired policy, as in the third figure, to a new trajectory tau plus delta tau, as in the fourth figure. The update should satisfy the constraint that the new trajectory tau plus delta tau should be safe. Once obtained a set of synthesized safe trajectories like tau plus delta tau, we can use them to train the naively repaired policy. This is the workflow of our approach. First, we use naive policy repair to obtain a safe policy that generates the safe trajectory tau. Then we transform the minimum deviation objective into an optimal control objective j, of which the decision variable is delta tau, which is an update upon tau. Those updated trajectory tau plus delta tau should not only satisfy the dynamics, but also satisfy the safety requirement. After updating a set of trajectories, we use them as training data to train the current naively repaired policy. If the trained policy turns out to be unsafe, we can use naive policy repair again to improve safety. Our case study is the autonomous driving simulation that we have introduced before. In the video on the left, we simply paired the policy with the safety controller. We can observe that this safety controller tends to slow down the vehicle after the vehicle skids out of the lane. The blue curve indicates the intervention from the safety controller. This is against our goal, as aforementioned, that the vehicle should move at a constant speed, 8 meters per second. After applying the minimally deviating policy repair, we obtained a policy that drives the vehicle as in the video on the right. The magenta curve is the vehicle trajectory. It shows that when the vehicle skids, the policy corrects itself smoothly without losing too much speed. Here, we evaluate the performance of the policies from multiple aspects. We evaluate how well the task is finished, mainly from the following metrics. Average speed. The closer the average speed is to the target speed, 8 meters per second, the better. The average distance of the vehicle to the middle of the lane. The smaller the distance, the better. The total time taken for the driving task in number of simulation steps. The fewer steps, the better. We evaluate the smoothness of the trajectories based on the variance of speed, variance of the distance from the vehicle to the middle of the lane, standard deviation of the speed changes in consecutive steps, the standard deviation of distance changes in consecutive steps. Smaller variance and the standard deviation indicate smooth navigation. Before the IC area is placed, no traction loss event happens. The initial policy drives the vehicle at 8 meters per second on average and keeps the vehicle close to the middle of the lane. After the traction loss event happens, the initial policy still maintains the speed, but the car skids out of the lane. It stays out of the lane for too long, as indicated by the average distance. It violates the safety requirement. The initial policy and the safety controller pair has the lowest average speed. As a result, the task time represented by number of simulation steps is also the longest. In terms of policy repair, both naive and minimally deviating repair are successful in finding safe policies. The naive policy repair algorithm generates a policy that behaves similar to the initial policy and the safety controller pair. The vehicle experiences significant speed changes and it takes longer to finish the driving task. The minimally deviating repair policy behaves similar to the initial policy in terms of maintaining the target speed, staying close to the middle of the lane, while producing a smooth trajectory. In summary, the minimally deviating repair policy outperforms the initial policy with safety controller and the naively repaired policy in almost all metrics. Additional case study can be found in the paper. Here is the summary of our paper. We use simplex architecture to provide runtime safety assurance. We define policy repair problem, which aims at avoiding frequent invocation of the safety controller. We provide a strategy that collects runtime safe control data for policy retraining. We further introduce the concept of minimally deviating policy repair to take into account both performance degradation and maintaining safety. We transform the policy deviation minimization problem into an optimal control problem that incorporates safety constraint. Our approach successfully produces learning-based controllers that accomplish safety while preserving the performance in finishing the tasks. That's the end of the presentation. Thank you.
Thank you very much. So I see there was a question in Slack. So Musa, do you want to ask it?
Yes. So actually, I asked that for policy repair, how do you collect the labeled data set?
Okay, at the runtime, actually the label is provided by the safety controller. If the current action, for example, at each time step, if the current action is certified to be unsafe, then the safety controller will provide a safe action for substitution. Right. So this is actually the whole system is always outputting the safe control. So the safe control actions are the ground truth label for the supervised training.
Thank you.
Any other questions? Please raise your hands. I have a question. So how much additional data do you need to actually perform policy repair?
Actually, it depends on the how much the deviation between the policy, the current policy, and the initial policy. And, usually, you need to have the policy, the way or the agent to finish the whole task and collect the average state and action pairs in the whole trajectory. And then if you change into another environment, you may have to collect the trajectory in that environment. So,
and do you do this online as the car is driving?
Yeah, while car is driving, we collect the training data, and but for training, the training procedure itself, you may have to put it offline.
Oh, okay. So the repair actually doesn't happen online.
In fact, the repair can happen online. Depends on what kind of optimal control algorithm we use in the minimally deviating policy repair. For some optimal control algorithms are online algorithms, so they need to execute the solved action at each time step and find out what kind of loss that incurs, and then optimize for the next action. So it depends on what kind of optimal control algorithm we use. Actually, in this paper, we used the iterative LQR, linearly quadratic regulator, LQR. It is an online optimal control algorithm. So actually, we solve the trajectories online.
Okay. We have time for one last quick question. If not, let me ask one quick question. Did you experience any kind of computational resource issues? Looks like you're doing a fairly heavyweight computation in the car.
Yeah, actually, it's true. That's for solving the optimal control problem. It is computationally expensive, and to implement the safety controller, you have to verify every control action in every time step. But it can be the overhead can be alleviated by simply simulate the control policy for the future time steps to see whether the vehicle will get into some unsafe area, right? So we don't need to solve for this existence problem.
Okay, thank you very much. Let's go to the next talk. So the next talk is Patriot, Policy Assisted Resilient Programmable IoT System. And it is presented by Musa Yahyazadeh. Hope I did it not too badly. Iowa University, University of Iowa.
Hello everyone, and welcome to my talk. I'm Musa Yahyazadeh from University of Iowa, and today I'll be presenting our paper Patriot, Policy-Assisted Resilient Programmable IoT System, which is a collaboration with my colleagues from Penn State, Syracuse University, and the University of Iowa. Today's agenda is to kick off by introducing programmable IoT systems and exploring their underlying security issues. Then, I'll explain our proposed runtime monitoring solution called Patriot, followed by our evaluation. And at the end, I'll briefly discuss Patriot limitation and future work directions, and conclude it by a summary. A programmable IoT system, similar to general IoT platform in its ecosystem, has those common three components. So we have a collection of IoT devices and network facilities to communicate with the computation and storage infrastructure. But the backend infrastructure features an app execution engine that runs IoT apps, enabling its users to provide customized automation in their IoT systems, And depending on the business logic, these apps send action commands to the IoT devices in order to perform some operations. For example, a command that says start recording on the camera. IoT apps are mostly trigger action programs, which in its basic form, once a trigger happens, it performs an action. The control logic between a trigger and an action can be a simple if-then-else rule or a complex machine learning-based model. Also, one trigger condition can make multiple actions at once. And once a trigger causes an action, that action itself can make a change in the environment and therefore may trip a trigger for another action. So the first trigger condition can have a long chain of cascaded effects. But why things can go wrong? Well, these IoT apps are usually obtained from the unvetted sources on the internet. As a result, they can be malicious, doing something unbeknown to the user, or they can just suffer from some hidden bugs. Or since these apps are developed in isolation and mostly not aware of the existence of each other, they may have some complex interplays that are unforeseen from the end users. So they can create some unexpected behavior in the programmable IoT systems. The unexpected behavior includes a variety of issues in such platforms. For the sake of time, I'll explain the first two. To understand insufficient access control, see this example. We have a smart lock with a battery as well as lock-unlock capabilities and a battery monitor app that displays a device's battery usage. In some platforms, an IoT app should ask for permission during the installation before accessing the device's capabilities at runtime. Here, it is asking for the battery. When granted by the user, the app can access it at runtime. But because of this coarse-grained access control design, instead of giving permission to the battery, the framework grants accessing to all capabilities of this device. So, the app can also sneakily unlock the door for an intruder. And Crosstab Interference happens as a result of complex interplays among the IoT apps. For example, fire extinguisher app gets triggered when a smoke detected and the temperature is high. Then the fire sprinkler goes off. This itself can trip water leak sensor and run leakage controller app, which then shuts off the water valve even though the fire has not been completely contained and causes home safety violation. In order to prevent such unwanted behavior, in a programmable IoT platform, we propose a runtime monitoring-based approach called Patriot that essentially observes the runtime information of the system, including the requested action, and based on the specification of expected or unexpected behavior as a set of policies, it either allows that action to be taken or simply drops it. The policies in Patriot is based on a restricted first-order past metric temporal logic with some aggregation functions that are useful in writing policies for IoT systems. This conscious choice makes us not only to express a rich set of policies, but also to enforce our policies efficiently by adopting the existing runtime monitoring algorithms. But the main challenge is that not all such IoT systems have a native backend support for the runtime monitoring. For example, they are using some proprietary backend that is probably in the cloud, or they have designed such that it is not easy to patch them. So Patriot is designed with that in mind. And there are many underlying components to make that happen. Some of these components that are inside this boundary are automatically generated by the others such that all necessary information is collected, evaluated against a given policy, and finally enforced at the runtime. Notice all is performed by the app execution engine itself. So it hits two birds with one stone. First, it doesn't need backend support for the runtime monitoring. Second, it avoids further runtime overhead for any unnecessary communication with the external entities. So everything is kept and executed inside the platform. Let's dive into more details in the instantiation of Patriot for SmartThings. SmartThings is a cloud-based smart home platform from Samsung that has its own proprietary backend which allows users to develop IoT apps on the web and install them using a companion mobile app. We have also instantiated Patriot for two other platforms called EVA ICS and OpenHAB that, although having the same principles, for more details, I encourage you to visit the paper. All right, Instrumenter is the component that automates the whole process and generate ready-to-be-deployed components for the app execution engine. So it takes SmartThings IoT app source code, which are written in Groovy language, and also a list of IoT action commands that are collected from SmartThings documentation, and then it generates the instrumented app for us. That also includes policy enforcement points. Essentially, Instrumenter parses the IoT app source code to identify the action commands in it based on the given command list. Then it guards the action using an if-then-else block such that its condition is a function call to a policy decision point. That's the place we check that the policies are maintained. And if not, we just simply notify a policy violation. So in real example at the bottom, Instrumenter identifies this unlock command and then uses a ternary operator to guard that. Eventually, if this action is aligned with the policy, it is allowed to be taken. Otherwise, nothing happens. But there is this policy decision point referred by this verify function. Well, Instrumenter takes the policies, and based on that, it generates a policy decision point for us, which also includes PIP that provides the current context information. So, by generating PDP, now an instrumented app can close the loop and verify that every action is compliant with the policies. But what does this PDP look like? Well, for each given policy like P1, it maintains a structure, which is essentially a tuple of current state related to this policy, previous state, and some auxiliary information needed for temporal operators and so on. The structure is necessary to keep memory of what has happened, because our policies can refer to the execution history through temporal operators. Then we have the update function that simply keeps this structure updated over the course of the system execution. Next, we have eval function that takes the updated structure as well as the current system context and returns true if the current context is aligned with the policy. And finally, a decision function that collects all the eval results and returns the conjunction of them. So if any policy violation happens, it returns false. Now, by considering everything I just told, under the verify function, there are still some considerations. First, we need PDP to be executed inside the app execution engine. So it needs to be implemented as an IoT app. But we know these IoT apps are executed in isolation, and they are not aware of each other. So this verify function cannot be called by the instrumented apps. Besides that, PDP also needs to have a global view of the instrumented apps for policy evaluation. Fortunately, SmartThings provide a parent-child architecture for smart apps that allows us to have PDP as a parent and all instrumented apps as children. This happens by adding some metadata to these apps, which is automatically done by the instrumenter. The next challenge appears because, as explained before, multiple actions can be executed for the same trigger. So we can end up with multiple instances of verify function for each requested action, where in one instance the policy is checked to be consistent for that action, but right before taking that action, in another instance, the state is updated such that the policy is not valid anymore for that action. This results in a well-known time of check to time of use issue that requires some sort of synchronization mechanism. Unfortunately, since SmartThings uses a restricted subset of Groovy language for security reasons, there is no backend support for that. But we realize that SmartThings uses blocking HTTPS calls, meaning it won't continue the execution until the response comes back. Based on that, we have developed our own lock management server that accepts authenticated HTTPS requests from PDP app in order to synchronize every call to policy decision point that comes from each requested action. So yeah, this is how everything is instrumented and deployed inside the platform itself. We evaluated Patriot against 3 test beds, one for each IT platform. Fortunately, all of them allow you to easily create virtual IT devices that can be programmed in order to control the experiment. We have created 17, 48, and 31 devices for these 3 testbeds and collected different IT apps from the internet or previous papers. And in some cases, we wrote our own apps to perform the evaluation. To show the effectiveness of Patriot, we managed to set up several scenarios in which different types of unexpected behavior happen. And then we wrote a set of policies that can successfully address those. These policies can be as simple as policy P1 that allows sending SMS only for a flood alert app and blocks SMS for the rest. Or it can be more complicated to include temporal operators. There are different blocks in the language like allow, deny, expect, and much more. The syntax and more examples are in the paper. Please take a look if you're interested in. In terms of efficiency, Patriot's runtime overhead is around 10% on average on these platforms, which is acceptable for many IT applications. And to dissect these overheads, you can see the synchronization overhead in each instantiation on the right graph. Among them, SmartThings instantiation has the highest lock overhead. That can be justified for its non-native synchronization support and the fact that it has to use HTTPS to handle that. Comparing our policy language to metric first-order temporal logic, it neither supports quantification nor arbitrary function symbols, but it is sufficient to express existing IoT policies and also necessary for the efficient monitoring. Also, Patriot policy language is not designed for IoT novice users, so for better usability, it can be improved by having a user-friendly front-end language on the top of that. It also doesn't support checking that given policies are consistent. So there are some room for improvement there as well. Patriot currently supports centralized architecture, which is common among IoT systems, but having a decentralized version that can decompose policies and enforce them consistently would be interesting. Notice that Patriot needs all third-party services to go through the app execution engine. Otherwise, it needs native support from the backend. And just a quick recap. I have discussed Patriot that can prevent a variety of unexpected behavior in programmable IoT systems at once. It is general enough to be instantiated for different IoT systems, and we did that for 3 of them. And we evaluated Patriot to show its efficiency and effectiveness in addressing unexpected behavior in programmable IoT systems. Thank you all, and I'd be happy to take a few questions.
Thanks, Musa. I didn't see any questions in Slack. Still don't. Any raised hands? While people are thinking, let me ask a quick question. So I assume there is concurrency between those apps. And when you specify the policy, how do you take care of that? So is it semantically taken care of? Do you have to encode it in the policy? What do you do?
So for the concurrency, actually, as I mentioned in the presentation, so we are using a locking mechanism. So for each contemplated action, what we do is before going to the policy decision point, we use a kind of lock mechanism to make sure that whenever we are in the policy decision point, the context, everything, the state is not going to be changed by the other other actions that goes into the PDP. So this is how we are actually preventing that.
Okay, did you see any performance hit from that?
Yes, so for locking mechanism, as you saw in the graph that I provided, for smart things, because it doesn't provide any native support for synchronization, we have the most locking overhead. But for the rest, it was really kind of moderate, I would say.
Okay. Since I don't see any more questions, we can go to the next talk. Thank you very much, Musa.
Sure, thank you.
All right, so the next talk is runtime verification of autonomous driving systems in Carla, and presented by Eleni Zapridou. Please go ahead.
Hello, I am Eleni Zapridou from EPFL, and I will present to you the paper Runtime Verification of Autonomous Driving Systems in Carla, which is joint work with Professor Edgio Bartocci from TEUB and Professor Panagiotis Katsaros from Aristotle University of Thessaloniki. Autonomous driving systems are complex in design, they involve various interactions with their environment, and they can face multiple different scenarios. Therefore, systematic testing is highly costly and implies safety risks, whereas formal verification does not scale and cannot be applied to realistic cases and scenarios. This is the reason why companies widely use simulators for their validation, such as DeepDrive, Carla, Waymo, and others. These simulators enable testing of autonomous driving systems in realistic urban driving scenarios with complex dynamics. We worked on the Carla simulator, which allows simulations in synchronous mode, where every time step is updated upon a client request. In this way, the client script can receive signals for simulation traces, and we ensure that the simulation time step is synchronized with the simulation physics that run in the server. Although these signals contain various information about velocity, acceleration, locations of the car, and so on, it is hard to actually interpret them with respect to the requirements of the system under design. Recent advances in online monitoring of signal temporal logic, though, allow us to check if the signals fulfill these requirements. We propose an STL monitoring approach based on the recently introduced RTAMT library. We can verify at runtime scenarios of Carla by obtaining a robustness signal which expresses how close the simulation is to violating the requirements. To provide you with a little bit more of a concept, we run Carla in synchronous mode in order to monitor all the events and not to lose any simulation steps, and in every step we send the updated signal to our RTAMT monitor. The monitor then checks at runtime how far the signal measurements are from violating or fulfilling the requirements and returns the corresponding robustness. To experiment with our technique, we build a simple adaptive cruise control system which is enabled if it senses a preceding vehicle. Then it computes the target velocity that the host car should have at the next time step to smoothly follow the preceding car, but without violating the safety requirements. The target velocity is computed according to the velocity and the distance from the preceding car. Then it is translated into throttle or brake via a PID controller. On the slide, you can see the PID controller aiming to compute the throttle or brake, which will achieve the target velocity for the controlled car. When designing a PID controller, it is important to understand how to improve the system's performance. In general, by increasing the proportional gain, we achieve a proportional increase of the control signal. This way, the system reacts more quickly, but it tends to exceed its target and overshoot. The parameter of derivative control affects the capability of dumping, which is important to decrease overshoot. And the value of integral parameters affects the capability to limit the steady error, but the system may show oscillations if it is not properly tuned. Our runtime verification approach can help to adjust the three parameters to ensure the system's robustness. Choosing the right PID parameters might be challenging, but it is also crucial for the system's robustness. In our case, while experimenting with different PID parameters, we checked the main requirement of our system, which is that the two cars should always hold the minimum safety distance. We observed that with the first set of parameters, violations occur at the third and every next time the cars stop due to a stop signal or a traffic light, for example. The second set of parameters, though, solved this problem, and this is why it was chosen. You can see the robustness signal on the slide for one of the scenarios that we tested while tuning the PID controller. Tuning the PID controller showcases how runtime monitoring can help from the very first steps of the system's design. But apart from the design space exploration, our approach can be also used to monitor the simulation and check if it violates any of the requirements. For our ACC system, we set the requirement that the relative difference in the velocities of the cars should not be too high. We observe violations after stop signals and green traffic lights. But this is not a problem because in stop signals, when the host vehicle stops, the preceding has already moved ahead, causing an excessive difference in velocities. When at traffic lights, when they turn green, the host vehicle needs more steps to start accelerating, and the velocities difference is also increased. Therefore, these events happen due to usual driving incidents and do not actually violate our system. The requirement is thus satisfied, and also we can observe that robustness raises as time proceeds, showing that the ACC adjusts to acceleration changes of the preceding vehicle. Additionally, we set the requirement that the host vehicle should not accelerate sharply unless this behavior follows a sharp deceleration of the preceding car to guarantee that the host car does not show large fluctuations in acceleration, but it follows a smooth motion. The ACC fulfills this requirement, although the robustness in some steps is low. Our threshold G depends on the set time headway, and so by adjusting it, we could find the lowest time headway that still fulfills the requirement or a higher time headway for which the robustness is increased. We would also like to mention some previous approaches that are related to our work. The Verif AI toolkit analyzes simulation traces of systems with machine learning components. It performs also in Carla similarly to our technique. Verif AI aims to address the absence of specification for perception components, the analysis of machine learning components, and environment modeling. It works through offline monitoring in metric temporal logic and outputs falsifying traces. Such an analysis is also possible in our case, since RTAMT can be used for both offline but also online monitoring. Worth to mention are also S-Talero and Bridge tools for sensitivity analysis and falsification testing over Simulink traces. Sensitivity analysis of model robustness to STL requirements is based on uniformly varying model parameters, whereas falsification looks for an input signal that violates a requirement. To conclude, we propose a technique for the validation of autonomous driving systems based on online monitoring STL specifications. Our approach allows the design space exploration of such systems, uncovers undesired behaviors, and checks the specified requirements. This work is a first step towards additional contributions that will allow testing and verification of autonomous driving systems with machine learning components. You can visit the link on the slide if you want to see in detail how our monitor was developed in Carla client scripts. Thank you very much for your attention, and please ask any questions you might have or contact us at the forums.
Thank you very much. So again, I didn't see any questions in Slack and no raised hands. So let me go first. So you specifically target Carla. Compared to other platforms, including Realcar, I'm sure there are things that Carla makes easier and maybe some things Carla makes it harder. So what are the additional challenges working with Carla specifically?
So what was hard in Carla was particularly to find a way to run the exact same scenario multiple times. So for example, run it once with one set of PID parameters and then run the same with another set of parameters. Because for example, in every time you run the scenario, you can have different times on the traffic lights and so on. So you cannot be sure that you have the exact same. But I think that recent updates on Carla are addressing this point. So this is really good.
Since I still don't see any raised hands, so suppose you want to move your tool to a different simulator. How hard would that be?
So I think that as soon as you can have a simulator that can guarantee to give you a signal of the data that you need for your requirements, and you don't lose any events, I think it wouldn't be hard to combine it with RTAMT.
Okay, thanks. And now I see a question from Alex. Please go ahead. Alexander?
Oops. Yeah. Can you hear me?
Yeah.
Yeah. So actually, you asked questions I was going to ask about Carla. Maybe I have a follow-up questions on Carla. So you said basically you said that there was problem of determinism with the Carla simulator, that you could not ensure that the same set of parameters would return the same simulation. Is that right?
Yes.
Okay. And you think this might have been solved in the latest version?
Yes, I saw that they have done some improvements in the recording tool that they have, so that you can record the simulation and then run it again and monitor it again.
Okay, so there's no way of setting some seed somewhere that would ensure that like the random generator in the simulator would reproduce the same random numbers, something like this.
At the version I used, no, I'm not sure if they have included now.
Yeah. Okay, and just a similar question to Oleg. Did you actually try another simulator before choosing Carla?
Excuse me, I didn't hear you.
Did you experiment with other simulators before Carla, and what made you choose Carla instead of the other ones, if that's the case?
We began with Carla because of the synchronous mode it provides, because we thought it is useful. But I think that as soon as you can get the signals, you can combine it with RTMT, since it's just a library. So you can also use the approach on other simulators as well.
Okay, thank you.
All right, I think we should move on. Thanks for your presentation.
Thank you very much.
And the next talk is Soter on ROS, Runtime Assurance Framework for ROS, and presented by Sumukh Shivakumar. Please go ahead.
presenting SODR on ROS, a runtime assurance framework on the robot operating system. This work is a tool paper that presents an implementation of the SODR framework for building safe distributed mobile robotic systems, or DMR systems. So let's start with some motivation behind this work. The safety of DMR systems cannot always be guaranteed at design time. This is especially the case in the presence of complex, off-the-shelf components in robotic systems, specifically with the rise of ML components for autonomous systems. We ideally want to use these components to their full extent, but simultaneously need to ensure the safety of the system. The problem is that these components often cannot be easily verified. For this reason, the design of runtime assurance components has become an integral part of the development process of distributed mobile robotics. Runtime monitoring is essential for a number of reasons, including maintaining situational awareness, assessing the health of a robot, and most importantly, detecting any irregularities at runtime. This also enables the ability to deploy any necessary countermeasures when such irregularities occur. The way runtime assurance components address hard-to-verify components is by having a safety mechanism that brings the system from an unsafe state back to safety. Once the system is safe, the safety mechanism is lifted and the system operates as normal. So SODR is a runtime assurance framework that works in this spirit. The main idea of the SODR framework is to build DMR systems with runtime assurance modules based on the simplex architecture. Briefly, a runtime assurance module, or an RTA module, based on simplex has two controllers, an advanced controller, the AC, and a safe controller, the SC. It also includes a decision module that implements switching logic between the AC and the SC. The AC is used for operating the system under nominal circumstances. This is usually an optimized controller based on advanced heuristics or complex learning-enabled components. This makes it difficult to provide any guarantees on the behavior of the AC, however. And so, to guarantee the safety of the system using these controllers, the system can always default to a certified backup controller, which is the safe controller, that takes control over operating the system when anomalies in the behavior of the advanced controller are detected. The decision module is responsible for deciding whether it is necessary to switch from the advanced to the safe controller to keep the robot in a safe state. It also importantly decides when to switch back to the advanced controller to utilize its high performance in order to optimally achieve the objectives of the robot. So in SODR, all of these components are built using the P programming language, which is a verifiable language designed for writing asynchronous event-driven code that can be compiled down to executable code. The P language is used because in DMR systems, components within and outside of the robot are communicating asynchronously. So now, the goal is to take this framework and apply it to systems built on the robot operating system. This brings us to SODR on ROS, an implementation of the SODR framework on the robot operating system. SODR on ROS maintains a very similar approach and allows developers to implement DMR systems end-to-end while including RTA modules to provide runtime assurance on various components in their system. The framework is built using the P programming language and uses the simplex architecture for the specific RTA modules. It's important to note that while our implementation of SODR maintains a similar approach, we add a few extensions. Namely, we added a refactorization of SODR to support portability onto various robot SDKs. This refactorization separates the software stack implementing the robot from the actual robot SDK being used. This is all implemented in P, and it allows us to provide a robot implementation with formal guarantees on the behavior of the interacting components. This also allows us to easily port this framework onto other robot SDKs. The refactorization also includes a separation between the implementation of the robot's RTA logic and the actual advanced controller and safe controller implementations used in these RTA modules. This allows us to easily link the calls of the advanced and safe controllers in the RTA module to external implementations of the controllers. We also added a concrete integration of the SODR framework onto the widely used robot SDK, ROS. We provide an implementation of a software interface that implements the communication with the ROS SDK. The integration onto other robot SDKs can be done in a similar fashion. So now let's discuss the SODR on ROS architecture. We will first outline the main components of the framework and how it is implemented. The framework itself is comprised of 3 layers: the application layer, the software stack, and the robot SDK. The application layer contains the task planner, which is where the programmer implements application-specific goals. It is implemented in the P language as a P state machine. The second layer is the software stack, which is reusable for all applications. Here the software stack consists of 3 predefined P-state machines: the robot machine, the motion planner, and the plan executor. Additionally, it includes the decision modules, which are application-specific P machines used by the motion planner and the plan executor. The robot P machine serves as the interface between the task planner and the motion planner of a robot. It processes tasks and forwards them to the motion planner. The motion planner P machine computes a plan to execute a task. A plan is a series of waypoints to a destination. The motion planner is an RTA module, and depending on its decision module, the plan is computed by an advanced or safe planner. The plan executor is another RTA module implemented as a P machine and is responsible for executing the path. It also consults a decision module on what controller to use during execution. Once the plan has been executed, the plan executor informs the motion planner and waits for the next plan to be sent. And the final layer is the robot SDK. The software stack is built on top of a library of C++ modules. The library contains all external functions that the programmer implements for the decision module monitors and the RTA module controllers. Now, we will illustrate how to use SODR on ROS framework more concretely using one of our case studies, a drone surveillance protocol. Here there's a single drone exploring a grid with the walls on the boundaries of the workspace. The goal is to explore the workspace without ever colliding with any of the walls. The terminal windows shown are used to compile the SODR on ROS application, launch the gazebo simulator, and monitor the state of the robot during the execution. You can find this implementation along with other case studies on our webpage. So let's start with the task planner for our drone surveillance case study. To implement the case study, the programmer must first implement the application level goals in the task planner. We can see in this P code that we start by declaring our drone surveillance task planner machine. The P machine has 2 states, init and start surveillance. In the init state is where relevant workspace information and all robots are initialized. On completion, the task planner transitions to the start surveillance state, where destination information is sent to each of the different robots one by one. Now let's move to the software stack, which is reusable across different robotics applications. Starting with the robot machine, it starts in the init state by initializing the robot with ROS and creating a local instance of the motion planner. It then proceeds for the wait for destination request state, where it waits for the task planner to send a task event. Upon receival, the robot machine transitions to the process destination request state, in which it sends this information to the motion planner. The motion planner starts by first initializing its corresponding robot and the plan executor P machines. It then goes to the wait request state, waiting for a task from the robot machine. Upon receiving a task, it goes to the compute path send to plan executor state, where it uses an external call to the open motion plan library's motion planner and sends the plan to the plan executor. The last element of the software stack is the plan executor, which is defined as an RTA module. When initialized by the motion planner, the plan executor saves its motion planner and robot information and creates a decision module, after which it transitions to the wait request state. Upon receiving a plan from its motion planner, the plan executor transitions to the execute path state. For each step of the path, the plan executor queries its decision module on which controller to use. Depending on the robot's location and the motion plan provided, the decision module will send a safe controller or advanced controller event. The plan executor will then use the corresponding controller to execute the plan. Upon receiving the plan and completing it, the plan executor signals to upstream components that this plan has been finished and that the robot is ready to acquire a new task from the task planner. The decision module used by the plan executor has a parameter delta that looks ahead to the next delta waypoints of the drone's current motion plan and confirm that none are in dangerous locations. If the decision module sees that the robot will collide, it transfers control to the safe controller. The safe controller brings the drone safely back to the middle of the workspace. Delta is a configurable parameter of the decision module itself. Increasing values of delta causes the decision module to look ahead further into the drone's motion plan, and in turn makes its behavior more conservative in how close the drone can fly near the walls, as illustrated in the diagram. For increasing values of delta as displayed in blue, the drone's behavior is more conservative as compared to lower values of delta as displayed in red. The final layer is the robot SDK. The software stack, as mentioned, is built on top of a library of C++ modules. This library contains all external functions that the programmer implements for the decision module monitors and the RTA module controllers. The P language supports foreign function calls to C++, and so these C++ functions are callable directly from the P code of the decision modules, motion planner, and plan executor. Above here, we can see a sample P foreign function. This particular function is used to implement the advanced controller of the drone, and it is native C++ code. Here, we also make use of the raw C++ API in order to make calls directly to the robot in Gazebo. This is all possible because P can be compiled into C++ programs using CMake, which can in turn be compiled to ROS executables using the Catkin build system. In Soder on ROS, we also implement a second case study. We implement a robot delivery case study. Here we demonstrate the ability to have multiple robots running asynchronously using decision modules over multiple monitors. In this case, we have 2 robots with 3 RTA modules for battery safety, geofencing, and collision avoidance. For more information on how we implemented this case study, please visit our site. So in all, in our work, we presented a framework for building safe distributed robotics with integrated runtime assurance modules. With Soder, the implementation of robot logic has been separated from the underlying robot SDK, making it compatible with many robotics platforms. For the future, we plan to provide interfaces for certain specification languages. We also plan to integrate the framework with a broader class of robotics platforms, planning tools, and simulators, and increasing the scope of our case studies. Thank you.
All right, thank you very much. I see a question from Mo Fugali. Please unmute yourself and ask it.
Yes, thank you. Thank you for the talk. This was the easiest talk to me because I work on robots and runtime verification for robots. So I have a couple of questions about these P machines that you add on top of your robotic stack. Do you encode them manually, or do you have a strategy to generate automatically these monitors?
Right now, it's done manually. So the programmer has these monitors that they specify depending on what RTA modules they want to write. But the goal is eventually to have it be auto-generated. Yeah,
exactly. Because from a roboticist point of view, we are not familiar with these tools, so it would be nice to be transparent. The other question that I have is about the overheads that you have for your implementation. Have you tried to implement your layer on the real drone or on the real robots? Because I saw the experiments in Gazebo, and Gazebo you can run it on any powerful machine, but then when you put on the robot, you have 4 cores on your robot, and you can't really intercept these overheads, let alone the fact that Gazebo simulator is not repeatable. So what do you think about that?
Yeah, so prior to this, actually, prior to even working with ROS, the original Soder work was actually done using Mavlink. And in that work, they did use actual drones. So it has been tested. This ROS one, we should, so far our case studies only cover simulations in Gazebo, but from what we saw using Mavlink, there wasn't any significant overhead by using that.
With the ROS or with the
with Mavlink. So for our ROS implementations, we've still only used the simulator, but you're right.
I do not recommend deploying ROS on your drone. That's just a side note.
Okay.
Thank you.
All right. We probably should move on because our program chairs have important announcements for us. So let me thank all speakers in this session.
I think we lost Oleg.
Right.
Or
I think I can see.
Do I have the problem with my connection, or?
I also can see
Okay,
Oleg's person.
so
Yeah.
he was
Yeah.
blocked. So I hope he's still around. But in any case, let us continue with the last 10-15 minutes. So basically, this was the last session of RV. And if you remember, at the opening of RV, we announced the best paper award candidates, and we wanted to close RV with the actual award winner. And also, we would like to take a few minutes to present some impressions about this year's RV and present some numbers. So let me share my screen. Can you see my slides?
Yes.
Okay, so we are talking about the really nice stuff, the awards. And actually, we will not start with the best paper awards, but we will start with the test of time award. So this is an award that has been established in 2018, and it is given to the most influential papers published at RV at least 10 years ago in the past. So let me say a few words on the selection process. There are two phases. There was a selection committee which consisted of me and Joe and 3 steering committee members, in which we tried to identify the 5 most influential papers. So we made a short list, and then we invited a test of time award committee consisting of distinguished members of the RV community to select the actual awardee. So this year we had a very strong committee consisting of Patrice Godefroy from Microsoft Research, David Basin from ETH Zurich, and Serdar Teshiran from Amazon Security. And the award, the Test of Time award for this year is the paper Valgrind, a program supervision framework from Nicholas Nethercote and Julian Seward. Unfortunately, these 2 authors could not be today with us, but I would like to say a few words about this paper. So many of you know and probably use Valgrind, and actually, to our knowledge, the first publication of Valgrind was in RV 2003. And if you look at the pure statistics, this is by far the most cited RV paper ever, with I think more than 600 citations. And then if you combine it with subsequent Valgrind publications, there are several thousands, I think more than 3,000 citations on this work. So this very influential work on the dynamic program analysis was basically started in RV. So congratulations to the authors, and it was quite interesting. Actually, I personally, before doing this research, I had no clue that Valgrind started as an RV activity. And now we are coming to the RV Best Paper 2020 award. So I would again like to give you a few words about the selection phase. So in the first phase, the shortlist was based mainly on review scores from the program committee, but we were looking really also about the comments. So sometimes the scores can be also a bit misleading. We wanted to see which papers really excited the program committee. And then we selected also a number of anonymous members from the PC committee to review nominated papers and select the best paper award. So to remind you, the 3 nominees are Empirical Abstraction from Vivian Ho, Chris Alvin, Supratik Di and Jimmy Lawson, Niraj Basnet and Hussam Abbas with their paper on logical signal processing, a Fourier analysis of temporal logic, Nastran Shafiei, Klaus Havelund, and Peter Melitz on actor-based runtime verification with Mesa. And just before I announce the winners and the winner, I would like just to say a few words. What excited the reviewers about these three papers? So for the empirical abstraction, they said it's a very innovative and surprising idea, and a very good example where some of the key RV ideas like instrumentation and collection of traces are used to learn automatically an abstraction of a program. For the paper on logical signal processing, a Fourier analysis of temporal logic, there was this exciting interplay between signal processing and logic, which is still largely underexplored, and which is creating quite a lot of excitement in the community. And for the paper on actor-based runtime verification with Mesa, this was seen as a paper with a very high potential and impact, and with a perfect example of distributed monitoring at scale with the real data, and that actually works well. So these are basically the reasons why these papers were selected as nominees. And so we will give as one of the runners up the best paper award nominee certificate to the paper actor-based runtime verification with Mesa. And also the other runner up is the logical signal processing, a Fourier analysis of temporal logic, which brings us to the winner, so to the best paper award of RE 2020, which is the paper Empirical Abstraction by Vivian Ho, Chris Elvin, Supratik Mukhopadhyay, and Jimmy Lawson. So congratulations, and let us all clap for the winners of this year. Do we have any of the authors present?
Yeah,
Maybe you want to say a few words?
Well, thank you for the award. Thank you for the award. I mean, we didn't expect it, so it's we really like this conference. And again, thank you.
We thank you for submitting this excellent paper to this conference. And also let me just mention that the Best Paper Award is sponsored by Springer, and that there is also a prize given by Springer that will follow. So we will contact you about this. So this leaves us now with the second part of these closing remarks, where Joe will present some facts and some numbers about this conference and some impressions from our side.
Thanks, Dan. So new this year, well, we were virtual. That's certainly new. I don't think that has ever happened with RV before. COVID-19 was the underlying dark theme to everything that's happening. One funny thing that did also happen, I don't know if this has happened in previous RVs, but we had a paper on monitoring the US election, which was unfortunately withdrawn. I think quite a few PC members were looking forward to reviewing that paper. But more seriously, this year, RV had a special focus on RV for autonomous systems. We had invited papers in RV for autonomy that were reviewed like regular papers. We had a special session on RV for autonomy papers, and as it turned out, all of today has been kind of a special autonomy day, where we had an RV for autonomy panel discussion with 4 panelists from leading industries in autonomy and 1 from academia. We had 5 tutorials that were presented on day 0 of RV, where 1 was an invited tutorial. We had planned a poster and demo session for the first time for RV. Unfortunately, COVID-19 reduced it to just 1 poster being presented, because it's not so much fun to do demos and posters virtually, which is, I guess, better than 0. So we look forward to having a poster and demo session hopefully next year if the 2021 chairs also want to do this. Okay. We had 3 exciting keynotes, which were very well attended. We had Lane Desborough from Nudge Blood Glucose Inc., who presented a talk on the physical side of cyber physical things, sharing his experiences through various industries on the importance of monitoring and verification in general. We had a very inspiring talk by Tom Hensinger from ISC Austria on monitorability under assumptions. This talk I kept mentioning to Dayan made me feel like I want to be a grad student again and read all his papers and do some very exciting work. And today we had a very exciting talk by Katie Ricks Campbell from University of Illinois Urbana-Champaign on autonomy. Fantastic failures and where to find them, designing trustworthy autonomy. So thanks again to all these keynote speakers for sharing their valuable time with us. And hopefully you as the audience enjoyed these talks as much as we did. Next slide. So some statistics, we had 43 submissions. We had 27 regular paper submissions and 16 short paper submissions. Of these, we accepted 14 regular papers, which is about 52% acceptance. We accepted 9 short papers, which is around similar numbers, and we had 1 poster. So those of you who look at the acceptance rate might be thinking that, oh, why are we accepting so many papers? But let me give you some more insight into how the reviews were done. The review process was single blind, and all but 1 paper received 4 reviews each. I want to speak to the high quality of the submissions here, and only 5 rejected papers had uniformly negative scores. 2 rejected papers had an average positive score, which is to say that our acceptance rate reflects that though we had a smaller number of submissions, these were uniformly quite high quality, and there was a lot of PC discussion and and we had to make some hard choices in figuring out which papers to select for appearing in the final proceedings. Most papers had vigorous discussions in the program committee before any decision was reached. So please don't go by just the scores that you see on the reviews. There was almost every paper had more than 10 or 15 messages exchanged about these papers before we came to any decision. Next slide. I wanted to tell you a little bit about the program committee composition. So we had 45 PC members with 2 PC chairs. We had 5 people from industry. We had 8 women on the program committee. We had 13 young researchers. This is kind of the continuing initiative of the SC to include more diverse representation on the program committee. And this fact that speaks to this is that several new PC members who had not served previously on the RVPC, we are quite happy that they were able to serve this time. We had diverse representation in various areas, including software systems, formal verification, distributed systems, cyber physical systems, security, autonomy, dynamical and control systems. And that kind of reflects in the program as well that we have papers from these kind of diverse areas in the RV proceedings this year. Next slide. Wanted to share some information about registrations. So I don't know if this was an effect of the conference being virtual, that people get a chance to attend that they wouldn't otherwise, but we had 205 unique registrations and 171 registrants on Slack. What was interesting is only about 29% of the registrants had a paper accepted at RV. So about 71% people were interested in the conference without having a paper in RV. There were about 181 people who indicated an interest in the RV for Autonomy panel. Based on the registration numbers, we found that the largest interest was on the first day, then the second day, and the third day. I don't know what to make of this trend, but maybe it has something to do with the fact that day 1 also had the most number of papers presented. So that's the numbers in registration. What happened on the ground? Actual attendance, I think all sessions were robustly attended by about 35 to 45 participants, which is comparable to the live in-person versions of RV that I have personally attended, and I think Dayan has attended also. We had about 50 to 60 participants in keynotes. So that's also something we were quite pleased about, that people could find time to attend in comparable numbers to in-person participation. From these numbers, what we seem to, we think that the conference seems to have growing interest and has new participants. So we see a bright future for this area, especially with the new challenge problems from autonomy and other areas that are coming through. Next slide.
So maybe if I can just comment a bit regarding this, I was really surprised by this very consistent flow that actually the attendance was not changing a lot from session to session, but actually this is probably some artifact of the virtual setting. The participants were changing a lot. And because we were a bit trying to monitor who is attending and whether it is the same people all over again, and this flexibility that the virtual conference gives makes it that you know, some people choose to go to some sessions, some other choose to go to other sessions, which in total gives kind of a steady flow of people attending the virtual conference, but actually there is quite a lot of variability that we observed.
So I think a good learning point from that would be for future conferences to maybe have some virtual component to kind of keep the nice things that we saw from this year. All right. So zooming in a little bit, we use Zoom as an audiovisual platform and Slack for immersive discussions. Zoom does provide high quality networking compared to other solutions out there, but we had a few early glitches on day 0 as we were still working out the kinks in the system. We were able to stream day 1, 2, 3 talks on YouTube live, and all sessions were recorded and we will upload them on YouTube. The RV panel will also be uploaded, but it will be unlisted because of the desire of certain industry participants. But we will place the link on Slack. So if you want to go see the panel, you can still see it on YouTube through an unlisted channel. We had lots of lively discussions on Slack for every paper. And I think it's a good thing to have this Slack workspace. I'm hoping that we are both hoping that these discussions kind of continue beyond the life of the conference and serve as ways for people to collaborate. There's also some interesting things on the Slack that we want to point your attention to. So there's a channel called Feedback to the SC. Please use this channel to give any further feedback on how to make the conference more visible, how to improve its rankings, how to increase the diversity of people who attend the conference, or any other suggestions you may have for improving RV. We would really welcome that, and the steering committee would really welcome that. If you want to complain about how Joe or Dayan sucked, that's fine. You can do that there as well. In addition to that, you can also—
And you can do this anonymously.
Yes, you can do this anonymously. That's the most important point. We also have a channel for posting basically job openings for PhD students. So advertising positions for PhD students or postdocs, and quite a few of us have taken the advantage of that. So please use that to advertise, to spread the word. I think this is also a good networking opportunity. We get to do this in in-person conferences, and we hope to reproduce that somewhat through this virtual Slack platform. Finally, we have this conference wouldn't have been possible without the hard work of many people. We want to recognize the following session chairs: Thomas Ferrer, Elias Falcon, Hussam Abbas, Dimitri Tretel, Nicolas Basset, Bernd Finkbeiner, Borzu Banakdarpur, Maximilian Schwenger, Hazem Torfa, Stefan Yakshik, Ezio Bartocci, and Oleg Sokolsky. Without your help, we could not have conducted these sessions in such an orderly fashion. And thank you all for doing the hard task of balancing Zoom questions and Slack questions and keeping everybody on time. So thank you for your terrific support. A round of applause for the session chairs, please. Okay. Next, there are these invisible actors who have made this conference appear seamless to most of you. And we would like to once again recognize Sarah Mohammadinejad, Nivedita Manjunath, Anand Balakrishnan, and Parv Kapoor. They made a commendable effort. For those of us in LA, it meant waking up at really early times. And for those of you in Europe, it meant sleeping at odd hours to ensure a smooth conference for everyone. So please give a big round of applause to these student volunteers. And finally, we also want to thank all the program committee members for very high quality reviews and high quality discussions on EasyChair. We want to thank the Anonymous Best Paper Award Committee for giving us extra reviews to the selected papers in a very short amount of time. We want to thank the Test of Time selection and award committees for their work on helping us select the Test of Time awardee. We want to thank sponsors Toyota for sponsoring the costs of the Zoom meeting, which is why we were able to have free registration for this conference. We want to thank Springer for sponsoring the Best Paper Award and providing free access to RV proceedings. I'm not sure, Dayan, what's the current status, but at least for this year, it should be free. And I think for the next 4 weeks, you should have free access to previous years as well.
Yes,
right?
so for the next 4 weeks, we have everybody has access to both this year and all the previous year's proceedings.
Yeah, and thanks, Dayan, for poking the Springer people about it till they gave that to us. And finally, we would really like to thank the steering committee for their support through all the new initiatives, all the crazy ideas that Dayan and I and others came up with, and being there for us and being there for all the RV attendees. So really thank the steering committee for their commitment and vision of this conference. And next slide. And I wanted to kind of close on the note that some things did not work. Not everything was rosy. So we had discussions on having an RV competition. Lots of initial discussions happened more than a year ago, and we had many interesting ideas. The general idea was to select focus areas for creating a competition. Maybe some of the focus areas could be code instrumentation, runtime monitoring, and create benchmarks in each. Unfortunately, the ideas did not come to fruition for this year because of one reason or the other, but perhaps this is something to consider and discuss for next year, and we would welcome the comments of the community on this. Please feel free to share them on Slack or through email, or just speak up in Zoom. And with that slide, I would like to invite you all, next slide, yeah, to LA in 2021. I will not be doing the hard work of being a PC chair. I'm very happy about that. But I will still be there to support as a local organization chair. And we look forward to seeing you in LA next year. And thank you all for your contributions to make RV 2020 a success. And thank you, my co-PC chair, Dayan. It was a pleasure working with you, as always.
The same. It was really a pleasure organizing this with you.
Right. All right. Okay. And with that, I would like to call RV to a close, and we would open up the floor for any questions or comments before we adjourn.
The steering committee would like to thank Dejan and Jill for the organization. I think you found a great format and the execution was great. So thank you.
Thank you.
Thank you.
I guess it's time to bid adieu, and thank you all again.
So thank you all. I would like to thank actually all the participants, because again, no conference can exist without all of you who attended, who were there to listen to all these very nice talks, and it was a pleasure to organize it.
All right. Thank you. Bye-bye. See you in 2021.
Thank you. Bye, all.
Bye.
Thank you very much.